everyone. Am I audible? I guess I'm audible.
Yes,
So,
Aditi.
yeah. So basically today I'm going to present about LongLLMLingua. Before that, it's the extension of LLMLingua. So we'll be briefly discussing about LLMLingua, which is compressing prompts for accelerated inference of large language models, which was accepted in EMNLP 2023. So basically, we all know that large language models are becoming one of the popular research nowadays, and people are trying to improve its performance by using various kinds of methods, such as chain of thoughts. But in order to do with this, it requires a longer prompt. So therefore, it's difficult to strike a balance between between the massive computation and the demand for longer prompts has become an urgent issue because of the limitation of the tokens. And that's why it's a high thing to how about using compressed prompts. So previously there have been researchers, similar kind of researchers, selective context, in which it showed that lower the tokens with lower complexity contributed less to the overall entropy of the language model, and hence they employed a small language model in order to compute the self-information of each lexical unit. And then they tried to drop the less informative content for the prompt compression, but there was many kind of limitations, which the first one is they could not do, they ignored actually the interdependence of the compressed contents. Like, for example, if they are removing the lexical unit, the sentence did not make sense. And they even neglected the correspondence between the large language model that is being actually targeted and the small language used for the compression, for the prompt compression. These were the limitations which this LLMLingua tried to solve it. So how did they try to solve it is they basically presented a budget controller. So given a scenario, and input prompt consists of question, instructions, and the demonstration. So they try to dynamically allocate different compression ratios to various components in the original prompts. And they even introduced the token level iterative algorithm for the fine-grained prompt compression, which is so that the information makes sense. And then they even propose an instruction tuning based method to align the distribution of both language models, the smaller models and the targeted ones. So we'll be discussing briefly about this in the coming slides. So moving ahead with just the problem formulation. So here is nothing but just to the gap between the targeted and the original should be less, and this is all this is a basic equation where they have used the scale divergence for the distance calculations. So moving on with the methodology, so here you can see that an original prompt is given, and then it's moved towards the large language lingua, where they have the budget controller. The second one is the iterative token level prompt compression and the distribution alignment. The black box LLM refers to the ChatGPT 3.5 and the Claude version 1.3 they have used for the large language model, and they get a compressed prompt. So for the budget controller, briefly talking about budget controller, why do we need it? Just imagine there could be multiple demonstrations in the original prompt in order to convey the information, but actually this you have to allocate different kinds of budgets to instruction or demonstration or the question. So in the original prompt, it consists of three things. So instruction and question are the most important one, and it should have the maximum number of budget rather than the demonstrations. But if we allocate the same type of things, it will affect the instruction and the questions, because demonstration could be multiple. So just imagine let's take that input is a small language model, MS, which is like either ChatGPT or Claude. And then we'll try to get just the demonstration compression rate for the demonstration only, given by equation number 2. That is like just calculating, here L refers to the number of tokens, and L instruction means the number of tokens for instructions, and same as L question refers to the number of tokens in the question. So we'll be subtracting it and getting just the number of tokens for demonstration only, and then we'll rank it in descending order, and we'll iterate it with and we'll just put all the demonstration set only till up to k into demonstration into multiplied with the tokens level, like just a specific number, and then later on we'll add we'll add the compression ratios for the instruction and the question, and hence we can see that in equation number 3 it's actually subtracting the maximum number of like which we have got from here, and that's how it's actually being formed, the budget controller, and the output would be the subset of demonstrations. Just one bit. And then we'll follow the iterative token level prompt compression, and got from the iterative token level prompt compression. Just 1 minute. So basically in here it is trying it has 3 equations. Instead of following the equations, we'll first see what it's actually doing. It's like once it's already get the small language model, the prompt from the budget controller. The next step is to iteratively token level prompt compression, and the equation number 5 basically deals with just giving the corresponding probability up to the point till compressed prompt, and then we'll try to set the compression threshold. Here you can see that in equation number 6, the delta phi is added to instruction and question. It is because it's the adjustment factor allocating more importance to this type of token level, and that's why it's not added to the demonstration. And lastly, it will append the compressed token via equation number 7, where it just uses only those tokens higher than the greater than the gamma. Yes, and then we will get the output as the compressed prompt. And then we'll go with the distribution alignment. It is basically to narrow the gap between the distribution of the large language model and that of the small language model used for the prompt compression. And here you can see that it's just optimization of the small language model, and that will actually minimize the expected average loss, and it will basically measures the output. So for this, they have just used like different types of data sets, and it was like for reasoning and in context learning, as well as the for contextual understanding, which was a new one that they have used, that is shared GPT, and for conversation they have used the archive March 27. So with the performance level, they have like briefly talking about this. So they have actually said that their ones like 5 times compression is better, and for the 3 times is better, and it was able to perform like slightly better than the selective context and GPT-4 generation. And for the case of like we can see that BBH is mainly due to challenging reasoning tasks, because it had a lot of reasoning questions which was not able to get it compressed and properly. And then you can even see in this case the 3x compression compression is better than the 2x. So following with it, this was just a brief recap of the LLMLingua, which was the extension of LongLLMLingua. So in this case also, they have actually focused with 3 challenges. The first one is like higher computational and financial costs, because like because calling APIs for companies which don't have much much budget, it's much more challenging. And then the second one is the longer latencies. It causes delays in generating responses or predictions. And the third one is lower density, the inferior performance caused by the extended window size. For the although the first 2 challenges were addressed in the LLMLingua, the third one was not being addressed. So as you can see with the figure A here, you can observe that that performance decreases as is decreasing as the number of noisy prompt increases. And with this with the figure B, you can see that this original prompt with the original prompt, that is the purple line, you can observe that for the first few at the beginning, the informations are more useful, and then at the end, not in the middle. So with this, we can, in order to preserve the key information, we need to focus more on the front and the last of the prompt during prompt compression. So the major contributions are like as follows. Like they propose a question-aware course to find compression method to improve the key information, and they also introduce the document reordering mechanism to reduce information loss in the middle. And then they even presented dynamic compression ratios to bridge the coarse compression and the fine-grained compression for adaptive granular course. And they also proposed the like post-compression subsequence recovery strategy in order to preserve the key information. So we'll be looking into it one by one. So just the problem formulation. Like previously, it consisted of demonstration instead of documents. Here, it's going to consist, because it's for the longer context, so you'll see document instead of that demonstration, and it consists of instruction, multiple documents, and questions. So the prompt compression system is like y is the original prompt, and y dash is the generated by the LLM, and here and this term is just for the regularization, and d is the distance between 2 distribution, and this distribution should be left, and they have used the KL. So the methodology is almost similar like LLMLingua, just that they have this subsequence recovery with the response, and we'll see how it's actually in the coming slides. So first they have like in order to improve the key information density in the prompt, they have done 2 formats. The first one is question aware coarse grain compression, and the second question aware fine grain compression. So with this you can see that like coarse grain means they're focusing on each document, not saying like it, yeah.
죄송합니다만 혹시 저만 오디오가 잘 안 들리나요?
저도 안 들립니다.
네, 살짝 노이즈가 낍니다.
그 아지트 학생 지금 목소리가 잠깐 안 들리거든요. 중간중간에.
Okay, I'll try to remove my earphone. Is
네.
it okay?
아니 뭐 아예 안 들리는 게 아니라 중간중간에 뭐 되게 소음에 묻히는 것처럼 소리가 들려가지고 그런 거여서 예. 다시 한번 해주시겠어요? 예.
Is it okay now?
네, 근데 뭐 일단은 좀 말씀해 보시면은
Okay, sorry.
고쳐졌는지 알 수 있을 것 같아요.
So can I continue from this current slide, or I have to go
네,
from
그렇게 해주시죠. 예.
Okay. So basically, As you can see with the figure, with the current figure, you can see that LLMLingua with recall 16, you observe that it only reaches up to 50%, indicating that it's not able to preserve key information during the compression. But also on the other hand, you can see as BERT on with the recall 5, you can observe that it's basically reaching up to 75%, where we can say that the maximum limit will be 75%. That is 4 times of the compression. And in order to calculate document level perplexity conditioned on the question Q, we need some kind of relevant information. So they proposed to use the restrictive statement in order to strengthen the interconnection of the question and the document, and which is referred in the equation number 2, which is just the regulatory term that actually mitigates the impact of the hallucination using the restrict is just for the strengthening the interconnection of the question and the care document.
죄송한데 방금 이 그래프에서 리콜이 어떤 의미인지 사실은 전 저 number of retained documents가 무슨 말인지도 잘 모르겠거든요.
Number of retained documents, they have actually used multiple documents. So number of retained documents, 1 means 1 document and 5 means 5 documents, as per I got to know.
예, 그러면은 저 retain 한다는 게 그러니까 원래 이 태스크에서 원래 입력으로 주어지는 게 20개의 다큐멘트인데 그 중에서 이제 되게 적은 수의 다큐멘트만 컴프레션을 위해서 사용을 한다는 뜻인가요?
They are like trying to compress each document and use only 1 document where it actually contains the correct answer. So they have to compress each and every document.
아, 예. 그 모든 다큐멘트를 다 컴프레스를 한다고 했는데 그러면 그 중에 한 개만 리테인 했을 때 성능이 이제 맨 왼쪽에 있는 그 점이잖아요. 그럼 그 한 개는 어떻게 선택을 하는 건가요?
With this ranking system they are using, which was over here. Actually, sir, they are trying to rank it. Yeah, like this type of ranking, getting from the budget controller.
저기 지금 K개가 다큐멘트의 원래 입력으로 주어진 다큐멘트의 개수이고 그게 이제 저 랭킹 시스템을 통해서 이제 리랭킹 된 게 R1부터 RK까지의 저 새로운 인덱스인가요?
And they are trying to rank it using the budget controller. Like budget controller actually identifies which one has to be compressed more and how much can it be compressed. So they are using the ranking system to reorder again which document is more important and which document is not important.
네, 알겠습니다. 네.
And then after they have used this question aware coarse grain compression, they again getting the question aware coarse grain compression, they again applied the question aware fine grained compression. In here, it's like importance of each token in the instruction, question, and K documents after the coarse compression. And in order to do that, they have used the contrastive perspectivity, and here as you can see with the equation itself, it suggests that it's the distribution shift caused by the condition of the question to represent the association between the token and the question, and hence you can see with this figure, more focus I've been driven towards the like with this line before that, and we can say that okay, this contrastive perplexity is working rather than just the perplexity, where every important tokens are distributed, and but with the contrastive perplexity, it's distributed only um, at the first part, because uh, this large language models tends to focus only in the first and the end. And then this, as I mentioned before, after information is gathered in the beginning or the end, and then they try to re-rank it and re-rank all the documents with their correspondence importance scores. And then next thing is to achieve additive granular control during the compression. So here you can see that here ND refers to the number of documents, and RK is the rank, and it is the importance score. And so we have to we have to bound this only with between 0 and 1, and that's why max and min is being used between 0 and 1. And this pi I is the compression budget allocated for a specific specific token xi. Is it not audible?
아니요. 가끔씩 노이즈가 섞이는데 어떤 경우인지 파악하려고 글 남긴 거라서 예, 신경 안 쓰셔도 됩니다. 예.
Okay. And the reason why they have used this term is that the more important a token will be, the smaller the fraction, which means higher budget for the document will be given, and hence like they achieve the additive granular control during the compression. So the next step is like the recovery statement. As you can see, the original prompt resembles like this, and the compressed prompt is like it's having the shortcut, and then the LLM response will also be the short form only. So we have to resemble this. So what basically they have done is they'll go through the original prompt, and they'll identify where it has actually been, and they'll try to map it out, and then they'll actually replace this word with the correct with the actual one, and that's how the recovery is going on. And this was all about the methodology part, and moving on towards the experiments. So for the data set and the evaluation metrics, they have used the three ones, that is like the natural questions, which has like question answering scenarios like ping chats, or and each question has like 20 documents, and long bench has like 6 task types. The first one is like single document question answers, and the second one is multi-document question and answers. Here multi-document is like maximum up to 10 documents, and then it's a summarization or like few short learning or code completion and etc. And then the zero crawls, like it has 4 task, summarization, question answers, and sentiment classification. For the baseline, they have used these retrieval based methods or the compression based methods. For the retrieval based methods, they have like used this 5 sort of retrieval methods, that is like that includes sentence part, OpenAI embedding, BM25, etc. And for the compression based method, they have used this LLMLingua, and to check whether it's and the selective context that we have discussed. Uh, so with this experiment, we can see that this LLM and selective context performs like much more poor than this LongLLMLingua for various number of documents. And we can also observe that the original prompt for the first document, it was just like like 75 5.7, which is like slightly higher than the LongLLMLingua. But on the other hand, like for the 10th document, it showed the performance gain of 17.1%. And we can also observe that 2 times compression was able to perform better. This may be due to the like not losing informations, but on the other hand, 4 times compression was slightly less than the 2 times compression. So next is the for the like number of tokens constraint. Here they only showed that okay, it was almost the same as even if it's like 3000 token constraint or 2000 tokens constraint, and was able to perform better like on all the baseline models. And for the evaluation study, they have said that even with the use of sentence part, which shows like slightly um, improved figures instead of using the ranking system, performs a little better. But on the other hand, like LongLLMLingua surpasses every of the base of this things, and that's how it is. And for the conclusion, like they have addresses all the 3 challenges. The first 2 were addressed by the LLMLingua, and the third one where the recovery was addressed by LongLingua, and they designed the 4 components with which LLMLingua demonstrated superior performance. And they have even showed that the compressed prompt can derive higher performance than the original prompt. That was all. Is there any questions?
네, 발표가 끝나서 질문해 주시면 될 것 같은데요. 제가 먼저 좀 질문 드리면 방금 그 첫 번째 논문이랑 두 번째 논문에 그러니까 제가 이해한 바로는 이 LLM 링구아라는 게 그 여러 개의 다큐멘트를 주고 어떤 그 사실관계에 대한 질문이 들어왔을 때 거기에 대해 그 정답을 맞추는 태스크를 푸는 건데, 그 다큐멘트가 너무 많아서 이제 컨텍스트가 너무 길어지게 되면 성능이 떨어지니까 그 컨텍스트를 어떻게 하면 이제 압축을 잘 할 거냐, 그런 문제를 이해를 했는데 그게 맞나요?
Like, sir, you're talking about like LLMLingua is only focusing on the demonstrations, but LongLLMLingua has like multiple of documents, and it's trying to compress it, and then once it's compressed, they're trying to find the exact like question and answers, and it's finding the exact answer.
So what is the demonstration in LLM Lingua? Is it kind of
No,
that
demonstration.
examples?
Yes, we can treat that as an example. Like,
그래서 LLM 링구아는 그러면은 저 퓨샷 그 example들을 컴프레션 하는 게 목적이고, 롱 LLM 링구아는 그럼 그 다큐멘트를 그 컴프레스 하는 게 목적인 건가요?
yes, sir, this is what I understood.
그러면은 LLM 링구아랑 저 롱 LLM 링구아가 풀려고 하는 문제 자체가 항상 다른 거 아닌가요? 그러니까 같은 문제 풀고 있는 게 맞나요?
Uh, I felt they are doing the same thing. It's just that LLMLingua and LongLLMLingua their context is a little different. Like LongLLMLingua is trying to use for like more big documents, and LLMLingua is just focusing on few ones, and that's why it is designed only to address the few um, just for the few length of the prompt, not the like with multiple documents.
아니 그럼 방금 전에 그 롱 LLM 링구아의 베이스라인 중에 하나가 LLM 링구아였잖아요.
Yes, sir.
그러면 이 롱 LLM 링구아가 풀고 있는 태스크들은 다 다큐멘트가 여러 개 있는 그런 이제 QA 태스크인데, 그럼 LLM 링구아는 거기에 어떻게 적용이 되는 건가요?
Just 1 minute. Mm. This is the LLMLingua, where like the original prompt is like this, and these are the demonstrations, and after it's like being compressed, it looks like some kind of these things. So basically, they are using like the chain of thought things, and after compression, like it just turned out to be few tokens only. But I still wonder. And for the LLM Lingua, it's like it's just giving this type of responses only, like after like the documents are like given, and then it's just mm, compressing the documents, and then just the question is like a single word answer.
이게 지금 LLM 링과의 결과라는 말씀이신가요?
This is long LLM Lingua, and this one was LLM Lingua.
네, 네, 근데 이 LLM 링구아 같은 경우도 지금 데몬스트레이션이 하나밖에 없는 거 아닌가요?
Uh, they have actually considered this as whole demonstration.
예, 그러니까 데몬스트레이션 하나만 컴프레션을 하는 건가요? 지금 요 예시에서는?
It feels so, sir.
말씀하신 걸 들어보면 LLM 링구아는 퓨샷 이그젬플을 컴프레션 하는 거고 롱 LLM 링구아는 그 부가적인 정보로 주어지는 다큐멘트를 컴프레션 하는 거다 이렇게 말씀하시니까 두 개가 아예 다른 문제를 풀고 있는 것처럼 들려가지고 근데 막상 같은 벤치마크에 대해서 두 모델을 비교하고 있잖아요. 그게 잘 이해가 안 된다는 뜻이거든요. 아, 혹시 답변이 좀 어려우시면 네, 괜찮습니다. 예. 그
So I'll let you know after I look into it, because before I thought like they are using the same thing like compression. That's why they have taken the benchmark as that. But maybe like before, like what I thought was they are treating the demonstration as a document, and that's why they have used the same benchmark. But
아, 네네,
now,
저도 그런 것 같아서요. 예.
like
그러니까
now I'm not.
첫 번째
Yeah.
논문에서 데몬스트레이션이라고 얘기했던 게 두 번째 논문에서는 다큐멘트로
Okay.
표현이 된 게 아닌가 싶기도 한데.
Yes, sir. Like it has been changed. Like instead of using this demonstration, they have used the document. And what I think is they have converted the demonstration into a document, and that's how they have used the benchmark. Because with like the first two was being focused on with the first LLM Lingua, and the third one was focused with the long LLM-Lingua. Basically, for long LLM-Lingua, they have done for the compression of the documents, which are much more higher than the demonstration, plus the recovery things, because recovery of the LLM-Lingua's output after the compression.
아, 그 리커버리 하는 거, 그 센텐스 리커버리였나요? 그 서브시퀀스 리커버리인가? 그게 차이점이고
There.
또 어떤 게 차이점이라고요?
And for the long documents, compression of the long documents rather than just the demonstrations.
Okay, so how do they deal with the problem? I mean, the length of the document?
The length of the document, they are first like dealing with the coarse grain compression, and then using this fine grain compression, and that's how like they are dealing with it, and then they are ranking it.
그, 예, 그 다른 분들도 질문 있으시면 해주시면 되고 이 랭킹을 한다는 게 그러면은 그 더 관련성이 높은 다큐멘트를 앞으로 가져오면은 더 좋은 성능이 나온다고 생각을 해서 그렇게 하는 건가요?
Yes, sir. This is what I felt so.
그 여기 근데 문장을 보면 information is gathered in the beginning or the end라고 돼 있잖아요.
Yes, sir.
끝부분에 또 있다는 거 아닌가요?
It's actually like from this, like in the original prompt, the more is on the first at the beginning and little on the end. So the middle one gets lost. So that's why they have used the contrastive learning to focus more on the beginning. So that they can, so that the information is not being reduced.
알겠습니다. 예. 다른 분들 질문 주시면 감사하겠습니다. 네. 질문이 없으신 것 같아서 혹시 이게 코드 데이터 관련해서도 적용된 실험 있나요?
Um, as far as my knowledge, I did not know exactly. Code, yeah, code data, yes, sir. The Java code they have used it for the Java code, just to compress it.
아, 자바 코드에 대한 어떤 태스크요?
They just try to complete the code.
아, 코드 컴플리션 태스크에서요?
Actually, predict the next line only.
알겠습니다. 예. 그러면 그때는 코드를 컴프레션 하는 건가요?
Yes, sir. I don't know why did they do that, but they just give the compressed prompt and then they asked it to predict the next line of the code. And then the LLM response will be the compressed code, which they will actually change it with the original one, original ground truth, and that's how they are ending it up.
아까 테이블 중에서 그 칼럼이 first, fifth, 뭐 tenth 뭐 이렇게 되어 있는 거 있잖아요.
Yes, sir.
칼럼에 따라서 지금 그 어떤 정보를 나타내고 있는 건가요? 첫 번째 그 다큐멘트만 주고 푸는 건가요? 그러니까 first 같은 경우는?
Yes, sir. Just the first document and then 1 to 5 and then 1 to 10 and 1 to 15th and 20th.
아, 네. 근데 그러면은 first만 쓴 게 리오더 한 거보다 성능이 좋잖아요. 지금 첫 번째 숫자 같은 경우, 두 번째도 그렇고요.
Yes, sir, because of the re-ranking system which they applied, where
네,
the first document is like more prone to the compression is, and that's why the first one is showing better.
저 first부터 저 20th까지 있는 저거는 리랭킹을 한 다음에 그 순서에 있는 다큐멘트까지 쓴다는 거 아닌가요?
Yes, they first they ranked it and then they reordered it and then they are using that first document, not the original first document.
아, 그러면 저거는 이제 첫 번째 것만 그래 쓰는 게 리랭킹 한 다음에 다 쓰는 것보다 좋다 막 그런 뜻인가요, 그러면?
Yes, sir.
좀 죄송한데 그러면 잘 이해가 안 가는 게 저 fifth까지 돼 있는 거 보면은 리랭킹을 한 다음에 1번부터 5번까지 쓰는 거잖아요.
Yes, sir.
근데 제가 왜 리오더보다 그럼 성능이 안 좋은 건가요?
Um, Sir, maybe because they are mixing it and that's why reorder is not, it's little less.
저기 테이블 1 그 캡션 맨 밑에를 보면 저 for results reported on the first to 20th에서는 리오더링을 안 쓴다고 되어 있는 것 같네요.
Okay. Um, mm. So what I thought was like for the first one, the reason why it's they haven't mentioned it clearly why it's like reorder is less, and what I thought was the first one document is showing more result, more better performance because it utilizes the ranking system. That's why. But if they're not using the reordering strategy, then
네, 저 리오더링이랑 랭킹이랑 다른 전략인 건가요?
Sir, I felt it's different, like ranking and reordering. I felt like I took that term as like ranking is used for first they have ranked it, and then the most important ones is the document one, and for reordering, I felt like they are just shuffling it up. I felt like that.
셔플링을 하는 게 무슨 의미가 있는 거죠?
Like just randomly, like not using this ranking system and just giving it. That was what I felt.
저 리오더링 스트래티지가 그냥 다큐멘트를 랜덤 셔플링 하는 거라고요?
I felt, sir. They have not actually mentioned it as far as I.
알겠습니다. 아까 발표하신 내용에서는 리오더링이 인포메이션 로스를 줄이기 위해서 한다고 말씀하셨던 것 같은데 뭔가 지금 약간 착오가 있는 것 같긴 합니다. 예. 그 질문 있으신 분들 아무도 오늘 질문이 없어 제가 혼자서 지금 악역을 담당하고 있는데 궁금한 게 없으신가요? 네, 질문이 없으신 것 같아서 그럼 마무리를 해야 될 것 같습니다. 근데 그 아디티 학생께서는 지금 발표 중에 이렇게 질문들에 대해서 제가 생각하기엔 좀 충분히 답변이 안 되는 것 같아서요. 그 질문했던 내용들에 대해서 그 조금 정리를 해주셔가지고 그 오늘 그 공지 메일에 팔로우 메일로 보내주시면 그 세미나 참여하신 분들에게 좀더 잘 이해가 될 것 같습니다. 그거 좀 부탁드리겠습니다.
Okay, sir.
네. 그럼 오늘 발표 준비하느라고 수고하셨습니다. 감사합니다. 다음 주에 뵙겠습니다.
수고 많으셨습니다.